Hello everyone. Today, we are introducing a new framework for building autonomous GUI navigation. We call it OVIS. This research, presented by the Alibaba Group and Nanjing University, focuses on two key innovations: Agentic-Q estimation and stepwise policy optimization. Let's dive into how we are enabling AI to navigate the web as effectively as a human. At the heart of our approach is OVIS 2.5-9b. This is a multimodal model designed to browse the web, perceive interfaces, and act just like a user. The core innovation here is a shift in feedback. We are moving away from sparse, trajectory-level rewards to dense, stepwise feedback using something we call Agentic-Q estimation. The result? It's a classic case of David beating Goliath. Our compact 9B model achieves state-of-the-art results on Web Voyager and ScreenSpot, significantly outperforming massive proprietary models like GPT-4o and Claude 3.7 Sonnet in navigation tasks. So, why is this difficult? Traditional methods treat long web browsing sessions like a black box. Imagine an agent taking 50 steps to solve a task. If it fails at step 50, we get a 0 reward. But did it fail because of a mistake at step 1 or step 49? We just don't know. This represents delayed feedback. On top of that, getting human experts to annotate every single click is expensive and non-scalable. And the live web is unstable. 404 errors and lag introduce noise that confuses the model. Our solution is like turning on a flashlight in a dark room. Standard RLVR is outcome supervised. It only looks at the final destination. The OVIS framework is process supervised. We assign a value, or a Q-score, to every single step in the journey. Whether the Q-score is 0.2 or 0.9, we judge the quality of every action via Agentic-Q estimation. We don't just judge the destination, we value the journey itself. To achieve this, we use a three-stage pipeline. First, we have the cold start, where we perform supervised fine-tuning on grounding data to teach the model the basics. Second is Agentic-Q estimation. Here, we train a self-supervised critic. The model generates data, propagates success or failure signals backward, and learns to judge its own actions. Finally, we have stepwise policy optimization. This is where the actor refines its policy, learning from the Q model's feedback rather than interacting directly with the noisy live web. Let's look closer at Agentic-Q. We use backward propagation of reward. If the final step is a success, we propagate that positive label back through the previous steps, from finding info, to scrolling, to clicking. We also use technical refinements. We apply a sliding window to focus on recent history, preventing entropy collapse. And crucially, we use action focus. The Q model ignores the agent's internal thoughts and grades only the physical action, like clicking a Buy Now button. For the optimization phase, efficiency is key. We decouple the training loop from the live web. The live web is slow and noisy. So, instead of learning from the internet in real time, our policy, the actor, learns from the Agentic-Q model, the simulator or critic. This creates a fast, stable training loop. We use stepwise variants of algorithms like GRPO, RLOO, and Reinforce++ to optimize performance. To stabilize learning, we filter the raw generated samples through a funnel. First, an action filter discards samples if all proposed actions are identical. Next, a return filter discards samples where the Q-scores have low variance, as they don't provide good learning signals. Finally, we use adaptive group weighting to prioritize harder tasks. This ensures that only high-quality training signals reach the model. The results speak for themselves. On the Web Voyager benchmark, OVIS 2.5-9b achieves a success rate of 77.8%. Compare that to Claude 3.7 Sonnet at 76.7% and GPT-4o at 57.6%. We are seeing a 9 billion parameter model outperforming a proprietary giant by a significant margin. Navigation isn't just about planning, it's about precise clicking. On the screen spot benchmark, which measures grounding accuracy, Ovis dominates. Across mobile, desktop, and web platforms, we achieve an average accuracy of 92.45%. Compared to GPT-4o's 20.1%, this is a massive leap. Our optimization on navigation has fundamentally improved the model's basic grounding capabilities. It's not just about raw scores, it's about efficiency and generalization. On the online Mind 2 web benchmark, testing on websites never seen during training, Ovis scores 64%, beating both Claude and GPT-4o. Furthermore, Ovis is faster. It solves tasks in approximately 13 steps, compared to 22 steps for the baseline. That means Ovis solves tasks 40% faster. Let's look at a real-world behavior we call the boundary traversal phenomenon. The task was to find the price of an iPhone 14 on Apple.com. The agent spends 34 steps searching internally, clicking menus, using the search bar, but hits a roadblock. The item is delisted. A standard agent might give up or loop endlessly here. But at step 35, something amazing happens: metacognition. The agent realizes, I cannot find it here. I must search externally. It autonomously navigates to Google.com to search for the price, even though it was originally told to look on Apple.com. It breaks the rules of the specific instruction to satisfy the user's underlying intent. To summarize, Ovis redefines efficient autonomy. We achieve data efficiency by generating our own training data. We ensure training stability by decoupling from the noisy web. And we prove scale defiance by beating 70B+ models with a 9B model. This is Ovis, stepwise precision, agentic reasoning. Thank you.